Welcome to The Explainer. Today, we're going to get into the invisible forces that literally power our entire world. We're talking about work, energy, and power. You know, the basic rules for how and why anything moves.
All right, so let's start with a question you've probably wondered about. Why is it that lifting a textbook is considered work in physics, but thinking really, really hard about a problem isn't? I mean, you feel exhausted after studying, right? So what gives? Let's dig in.
See, in the world of physics, work isn't about how tired you feel. It has a super specific definition. It all comes down to two key things: a force and some kind of movement.
And here's the absolute bottom line. For work to actually happen, something has to move. You could push against a brick wall with all your strength. You'll get tired, for sure. But if that wall doesn't budge an inch, sorry, but in physics terms, you've done zero work. No movement, no work. Simple as that.
And the math behind it is actually pretty straightforward. We've got this nice, clean formula. Work equals force times distance. W equals F times D. Let's run through a quick example so you can see it in action. Okay, so imagine you're pushing a box. You're applying a force of, say, 30 newtons. That's our F. And you manage to slide it 5 meters across the floor. That's our D. To figure out the work, all we have to do is multiply those two numbers. And voila! That gives us 150 joules. A joule is the unit we use to measure work, and also energy. It's named after a really important physicist, James Prescott Joule, and believe me, we'll be hearing his name again in a minute. But what happens when things aren't so straight on? Like, think about pulling your luggage at the airport. You're pulling the handle up and forward, right? But the suitcase is only moving forward along the ground. Well, it turns out only the part of your force that's actually in the direction of the movement counts towards the work. That forward pull is what matters. Okay, so if work is the action, then what gives something the ability to do that action in the first place? Well, that's energy. Energy is the fuel. It's the currency you need to spend to get any work done at all. And that's really the core idea here. An object that has energy has the ability to do work. Think about it. A stretched bow has energy, which lets it do the work of launching an arrow. A car's battery has energy, which lets it do the work of starting the engine. No energy, no work. Nothing happens. And speak of the devil, here he is, James Prescott Joule. This guy was a total game changer. He was one of the first to figure out that all these different things, like mechanical work, heat, electricity, they weren't separate things at all. They were all just different faces of the same thing: energy. I mean, that's a massive realization. So yeah, he definitely earned having the unit named after him. All right, let's dig a little deeper, because energy isn't just this one-size-fits-all concept. It shows up in different ways. For now, let's focus on the two big ones in mechanics. You've got stored energy and you've got motion energy. And this really breaks it down nicely. On one hand, you have potential energy, or PE. That's stored energy. It's energy that an object has because of its position or its state, like that stretched bowstring or a boulder sitting right at the top of a hill. On the other hand, you've got kinetic energy, or KE. That's the energy of motion. It's not potential anymore. It's happening right now. That's the arrow flying through the air, or that boulder as it's falling. So let's stick with that boulder for a second. While it's just sitting there, at rest, at the very top of the hill, it's packed with potential energy, 100%. But since it's not moving, it has zero kinetic energy. All that energy is just waiting. But the moment it starts to fall, something incredible starts to happen. That stored potential energy starts converting into kinetic energy, the energy of motion. By the time it's halfway down, it's a perfect 50-50 split. It's losing potential energy because its height is dropping, but it's gaining kinetic energy because its speed is picking up. And right before it hits the bottom, you can see almost all of that potential energy it started with has been transformed into kinetic energy. This is a perfect example of one of the most fundamental laws of the universe, the conservation of energy. Energy can't be created or destroyed. It just changes from one form to another. Now, let's take a closer look at that kinetic energy formula. You see that little v squared? That's the velocity. And the fact that it's squared is a really, really big deal. It means that an object's speed has a huge, outsized effect on its energy. So if you double an object's speed, you don't just get double the energy, you get 4 times the kinetic energy. And this ties right back to what we started with through something called the work energy theorem. It basically says the amount of work you do on something equals the change in its kinetic energy. So more work means a bigger change in speed. That little squared velocity is why speed is so important in everything from car crashes to hitting a baseball. All right, so we've got work, we've got energy. There's just one more piece to our puzzle: power. And power is different. It's not about how much work you do, but how fast you do it. It's all about the rate.
And here's the best way to think about it. Imagine climbing a flight of stairs. Whether you walk up calmly or you sprint up, you've moved your body the same vertical distance, right? So you've actually done the exact same amount of work. But we all know running feels way harder. Why? Because when you run, you're doing that same amount of work in much less time. You're using more power.
So when you boil it all down, power is just work divided by time. The unit for it is the watt, and 1 watt is just 1 joule of energy being used every single second. It's all about how intense the energy transfer is. Okay, so why do we care about any of this? Well, because these ideas aren't just stuck in a physics textbook. They're happening all around you right now, from massive waterfalls to the cells inside your own body. I mean, take a look at a hydroelectric dam. All that water stored up behind the dam has a ton of potential energy. Then they let it flow. That potential energy turns into kinetic energy, which does the work of spinning these giant turbines. And those turbines generate the electrical power that ends up in our homes, letting us use our appliances. It's this perfect chain of work and energy transformation. And it's not just out there in the world, it's happening inside of you too. The food you ate for lunch, that's just stored chemical potential energy. Your body converts that energy to do the mechanical work of, moving around, and it also does the work of keeping you warm. We are literally walking, talking energy conversion systems. All right, let's just do a super quick review of the big ideas. Work is a force moving something over a distance. Energy is what you need to do that work. It can be potential energy, which is stored energy that depends on things like an object's height, or it can be kinetic energy, the energy of motion. Then there's power, which is how fast you're doing work. And of course, the golden rule, the law of conservation of energy. You can't make it or destroy it, you can only change its form. So from a bouncing ball to a car engine, these energy changes are happening everywhere all the time. So now that you know the rules of the game, where are you going to see energy transform next? Thanks for joining us on The Explainer.